Okay, so we looked at how you calculate the losses, basically the voltage loss, and that should be nothing but change in the duty cycle multiplied by your input supply voltage, which is VDD. So, buck converter can also be modeled as a transformer. So, if this is IDD and output current is your I out. So, for ideal transformer, P out equal to PDD, correct, which means VDD so we know V out is D times VDD. So, what is IDD? D times I out. Okay. So, your output voltage is multiplied by duty cycle, but when you look at the current, then input current is multiplied by the load current, which is your output, which means, and D is, you know, it is mostly less than 1. So, input current will always be less than load current, and that is how you get very high efficiency. So, this V out equal to D times VDD is only true under no loss condition, which we already looked at. Okay. Otherwise, D times VDD minus V loss, but this IDD equal to D times V out is true for all conditions. Okay. So, it does not matter whatever the actual duty cycle or, so your current will automatically get scaled, but because it is a current, you are looking at a current. So, but when you look at the voltage, you drop the voltage in the resistance, this power stage losses, and that is why your voltage is not the actual voltage, but it will get supplemented, but current will always be the same irrespective of whether you are looking at a no loss duty cycle or duty cycle under the losses. So, now how we define the efficiency? Efficiency of P out over P in, and this is 1 for ideal condition and less than 1 for in reality when you have losses in the power stage. So, this can be written as V out into I out over VDD into IDD. So, what is this? D lossless, okay. D no loss. And what is this? This portion? Let me change the color. So, this is your D no loss. And what about this? 1 over D, which is a D actual, okay, which means I can define efficiency as D no loss over D actual. How do you find? So, which means you don't really need to measure the power, huh? You just look at the duty cycle, you can find the efficiency. But this is only true for conduction efficiency. Conduction efficiency means you are only considering the conduction losses which are occurring in the resistance, I square R losses. But if you consider the switching losses, then this formula won't be valid. So, this is true only for conduction losses. So, how can I find the lossless D? What is the loss actually here? I square R. So, if you make I 0, loss will be 0. So, under no load condition, you get the no loss duty cycle, and when you apply the load, you get the lossy duty cycle. So, you can easily measure it. So, just by changing the load, you can measure both D no loss and D, and take the ratio of that, you will get, and you know that D no loss will always be less than D, because D has to increase in order to compensate for the losses. So, efficiency will always be less than 1 or less than 100%. Okay. So, now let us go back to your power stage. So, this is so let us take an example where VDD is 1.8 volt, V out is 1.5 volt, and RP is, let us say, so for simplicity I am considering both RP and RN same. So, the total loss will be your the R resistance actually, because 1 minus D and plus D. So, D will cancel out. So, leftover will be. But if you have a RP and RN are different, then you have to take that 1 minus D and D factor into account, because in that case your losses will change, equal to 0.5 ohm, okay, and your RDCR equal to 0.5 ohm, and I load IL equal to 1 amp. Okay, so what is V out? V out is nothing but D times VDD minus V loss. And what is V loss? IL multiplied by Rp times d times Rp plus 1 minus d Rn plus RDCr equal to IL is 1 m. So, this will become 0.5, correct, plus 0.5. So, this is nothing but 1 volt, no sorry, 0.05, sorry, no, 0.5 is too high. So, 50 milliohm, correct. So, this is 100 millivolt. V out is already known, 1.5 volt, 1.8 minus 100 millivolt. This implies D equal to 1.4 over, how much is this? Sorry, yeah, 1.6 over 1 point. How much is this? 0.8. Okay. So, D no loss will be nothing but 1.5 over 1.8. How much is this? 1.5 over 1.8. 0.833. Okay. This implies delta D is 0.033 or 3.3%. So, you get 3% change in the duty cycle in order to compensate for the losses. And what about the efficiency? So, let us calculate both ways and see if we get the same. So, one way you know the input power, output power. Okay. What is the input current? IDD. Zero 0.833 multiplied by, sorry, 0.8. No, this, I think you guys did something wrong. That is 0.88, huh? Yeah. So, this was how much? 33, huh? So, you get, correct, 5.5%. So, your IDD is multiplied by 1 m, which is okay. PDD 1.8 multiplied by 0.88. How much is this? Hmm? 1.8, 1.6, huh? P out 1.5 watt. Efficiency is 1.5 over 1.6. 93.75%. Okay, if I am looking at percentage. Now, from D no loss over D 0.833 over 88. How much is this? 94.6. No, actually it should be same. So we took approximation there, that's why 93.75%. Okay, point. So I'll just put an approximation here. Okay, so in both the cases you get almost 94% efficiency. So you can calculate either way. If you know the power numbers, then you can just do P out by P in. If you don't know the power number, you don't have a way to measure the power, then but you can measure the duty cycle, then you can just look at the duty cycle by removing the load and then applying the load, and just take the ratio of that, you will get the efficiency under only conduction losses. We are ignoring the switching losses here. Okay, so let's see if the same 1.5 volt was generated from LDO. So what will be the efficiency? 1.5 over 1.8, which is 83.33%. So almost 10% decrease in the efficiency, which is not that bad. Now assume everything remains same, but V out is 0.9 volt, which is just half of your supply. Okay, so your losses will remain same because resistance is not changing, load is not changing. So from the same formula, only this factor will change. Okay, 1.5 will become 0.9. So 0.9 equal to D times 1.8 minus 100 millivolts. So D is 1 over 1.8. How much is this? 55.55. So or 0.555. We know under no loss it will be 50%. So you are seeing 5% difference. So efficiency is how much? 0.5 over 0.555. 90%. Correct? What will happen in case of LDO? So and now if you remember the efficiency curve, this is your V out, and this is your efficiency. What was happening when V out was increasing? LDO efficiency was increasing, but switching regulator was keeping very high. So that's why you get almost flat efficiency. You will see some differences because your output power is changing, okay, but losses are not changing. So there will be some differences in the power number, but Okay. But in case of LDO, what happens? Your dropout voltage is reducing when V out is increasing. So when your dropout voltage is very low, then this efficiency may be quite similar to your switching regulator, or it may be in some cases even better if your dropout voltage is too low. So let's say 50 millivolt also you are looking at dropout voltage. So we know where here we are losing 100 milliwatt in switching regulator because of this DCR and switch resistance. So which means if your dropout is 100 millivolt, that is the V loss. So if the V loss is same in the two cases, then efficiency would be same. Now if your dropout voltage is less than 100 millivolt, your LDO efficiency will be better than your switching converter efficiency. Okay. So that's the reason we prefer LDO only for low dropout, and switching regulator for smaller V out by V in ratio or larger dropout. Yeah, it will remain same, but the efficiency of switching regulator will improve. But when you hit a very light load, then switching losses will start dominating, and your switching converter efficiency will also start dropping actually in that case. But overall, if you look at the average efficiency, switching regulator will have a better if you look at the wider load range or wider V out by V in ratio. In both the cases, your switching regulator performance will be better compared to your LDO.